Now, it turns out that we have a perfectly logical way to multiply a matrix by a matrix. Okay, now this matrix is just our 0.9, 0.2, 0.1, 0.8 matrix, and this one is the same. No good reason that they should both be the same, but I can illustrate matrix multiplication as well with two of the same matrix as I could with two different matrices. So I'm going to use two of the same. Now, to multiply these matrices together, you would think maybe, okay, just multiply 0.9 by 0.9, and that's going to give you 0.81, so we put that in there, and then 0.2 times 0.2 is 0.04, and all that stuff. That's not real consistent with what we did up here, though. We saw that when we multiply a row by, we multiply things by multiplying rows by columns. So what we want to do is multiply rows of the first matrix by columns of the second. Well, the question becomes, which row times which column? Well, every possible combination. So that means the first row is going to multiply the first column, the first row is going to multiply the second column, the second column is going to multiply the second row is going to multiply the first column, second row will multiply the second column. Now the question then is what to do with those numbers. Rule is easy. If I multiply, say, the first row by the second column, well, I'm going to form a matrix over here that has two rows and two columns. And I'm going to put the product of the first row by the second column in the first row of this matrix and in the second column. So the row and column that I use here determine the row and column of where the result goes. So let's see how that works. You might not have picked all that up, but you know that's the way it works, and you might see that already, but I'll go through it in detail. Okay, we take the first row by the first column. What do we get when we multiply this row by this column? 0.9, 0.2 row multiplied by the 0.9, 0.1 column. Well, it's going to be first number in the row times the first number in the column plus the second number in the row times the second number in the column. 0.9 times 0.9 plus 0.2 times 0.1. So right there we have it. 0.9 times 0.9 plus 0.2 times 0.1. Now I put that here. This is in the first row and the first column of this matrix because I multiplied the first row by the first column when I multiplied these two matrices. Okay, now I multiply the first row by the second column. I'm going to get 0.9 times 0.2 plus 0.2 times 0.8. That's first row times second column. That goes in the first row, second column of this matrix. And there we see it, 0.9 times 0.2 plus 0.2 times 0.8. Similarly, multiply the second row by the first column, 0.1 times 0.9, right there it is, plus 0.8 times 0.1, there it is. Okay, and since that came from the second row, first column, I've got it in the right place, which is the second row of this matrix and the first column. Then I multiply the got losing track here, multiply the second row by the second column and put that result in the second row, second column. Okay? Now, of course, I do the arithmetic and add these up, and you can easily verify 0.9 times 0.9 plus 0.2 times 0.1 equals 0.83. There it is. Okay? And this calculation is going to give us 0.34. This calculation is going to give us our 0.17. This calculation is going to give us 0.66. Okay. Now, what happens if I multiply that matrix by 800, 200, our original number of sane and demented in this example? Well, it's very easy. You calculate it out, and you get these numbers, and when you do the arithmetic, you get 732 and 268. Okay, what's the significance of that number? Well, I can illustrate the significance of that number. Remember, when we multiply just this matrix by the 800, 200, we got 76240, right? Well, now, if I go another step and multiply the 76240 by this matrix, I get 732, 268. You can verify that. This completely matches this. So what's happened? Well, this multiplication is the original matrix multiplied by the original matrix. So the original matrix has been multiplied twice to get this matrix, okay? Whereas here, I took the original matrix and multiplied it by my population vector, and then multiplied that result by the original matrix. Well, again, to get here, I had to multiply twice by the original matrix. So whether I multiply twice by the original matrix, multiply the thing by the original matrix and then multiply that result by the original matrix, or multiply the original matrix by itself and then just multiply that matrix by the original population vector, I get the same thing. Now, when I multiply something by itself, what I get is the square. So this is the square of the original matrix. If I multiply the square of the original matrix by the original population vector, I get the population after two transitions. In the same way, I get the same result as if I did the first transition to get this, and then multiplied that by the matrix to get the number after the second transition. Now I go even further with this. What would happen if I squared this matrix? What would I get? Okay? Well, it turns out that this matrix embodies two multiplications by the original, and when I square it, I'm multiplying it by itself, so I'm multiplying two more transitions from the original. I would get the fourth power of the original matrix. Of course, that's consistent with your laws of exponents that apply to matrices just as well as they do to numbers and symbols. For the most part, negative exponents where you got a reciprocal, you can't do the reciprocal of a matrix. You can do what we call the matrix inverse, and that's similar, but it's not calculated in a way that you would expect. So we get to that, and we will get to doing that because this is extremely powerful. Okay.